I never do. All right, good morning. Today, let's get into FETs. We'll do a little bit of FETs. It's field effect transistors. It's not technically part of the syllabus in the sense we'll do a little bit of introduction. There is a lab associated with the JFET, and then we'll look at a little bit of the MOSFET also. Okay. All right, so let's see if this synced. Oh, wait. Okay, so FETs. All right, everyone. It's field effect transistors. Okay. We went over a little bit of, not a little bit, I have one slide dedicated to the invention of the BJT, the bipolar junction transistor. And that is, of course, a big chunk of our course, starting from next week, mid next week, I would say. But before that, we'll also learn about field effect transistors. Field effect transistors are so called because they rely on an external electric field, an external applied voltage. And there are primarily three kinds of FETs. Junction FETs, JFETs, MOSFETs, metal oxide semiconductor, and MESFETs, metal semiconductor. Each one of those is fabricated or manufactured a little bit differently. And the operation of each of these devices is also different. But they primarily rely on an external electric field, hence the name field effect transistors. Over the years, MOSFETs have become the de facto choice of building electric circuits or electronic circuits. Nowadays, nearly every IC, nearly every chip that we use in today's devices are all made from MOSFET technology. MOSFETs, when they were first invented, there's two kinds, PMOS and NMOS, and we'll look at those a little bit later. But it took a while for the manufacturing to reach a level where the devices were more power efficient, also of low cost. And so it took a while for it to catch on. But once it caught on, MOSFETs have several advantages that rendered it the de facto choice in modern electronic devices or modern electronic circuits. So again, we will look at it a little bit, but not a whole lot. In 307, you will primarily build circuits using MOSFETs. So you have an entire course dedicated to circuits using MOSFET technology or MOSFET transistors. Okay. We have a lab associated with the JFET, I believe it's lab 6. So we will look at that. And then MESFET is not something we'll go into too much detail. Okay. All right, so let's look at the basic construction of a junction FET, JFET. Now you can view this as sort of a top view of the device. Remember the silicon wafers we saw, right? And then if you're looking at it from the top, let's say you have this big silicon material, and then inside it, you would create a N-type material. Well, for this example, we're using N-type material, but you can create N-type as well as P-type, okay? So here, this is a N-channel JFET, and this one is a P-channel JFET. The N-channel and the P-channel naming comes from the fact that we're using N-type material to create our structure. So let's say we have a silicon wafer, and we create a N-type structure in there, meaning we're implanting a lot of what kind of atoms? Donor atoms. Donor atoms have an extra electron. It's an N-type material. It's a simple pop quiz. And in this N-type material, we would implant acceptor atoms, thus creating p-type material. Okay. And once we implant a p-type material inside an n-type material, we now have a p-n junction. In this case, we have two p-n junctions on either side, thus creating a channel in the middle. Right? There's a channel right there in the middle. And hence the name N-channel and P-channel J-FET. So the naming comes from the type of material that we use to create our channel. Okay, as you can see here, in an N-channel J-FET, the primary material is N-type, and then we implant P-type inside it to create two p-n junctions. Thus, the channel in the middle is N-channel. Same thing with the P-type material. You have a P-type material, and then you implant N-type, thus creating a P-type channel in the center. Okay, let's take a 10-second pause. Let me know if you have any questions. Yes. So there are some minor subtle differences, but primarily depends on the application. Depends on the application. These are well, I'm getting ahead, but we'll wait for a few more seconds before I talk about that. Any other questions? Does construction make sense? Right? So I was saying we have two p-n junctions, and so we have two depletion regions. Okay, two depletion regions in there. There's one right here, and the other one's right here. So there's two depletion regions. And when you connect this J-FET into an external circuit, well, actually, even before we connect it, the two p-type regions are connected together to form a single terminal known as the gate. So when we connect it to an external circuit, the gate terminal connects to both p-type material. Okay. So you see here, which is marked as G. G stands for gate. And the two far ends of the channel are labeled as drain and source. Drain and source. If you apply this to a water tap analogy, you have a source, you have a drain, and there is a gate that controls the flow of water. And in this case, that analogy fits perfectly. Except we're not talking about fluids, we're talking about tiny electrons. Okay, so we have movement of electrons, which of course is movement of current. And then we can control the movement of current or the flow of current by controlling the flow of electrons via the gate. Okay, and that essentially is the operating principle of a J-FET. You have a channel, electrons are moving through the channel, and you control the flow of those electrons by an externally applied electric field or externally applied voltage between the gates. So it's a three-terminal device. Unlike the diode, the effects of, not the effects, the field effect was presented as early as the mid-1950s, or 1954, 55. Okay, but an operational device was not created until much later. Okay, like an operating prototype. But the principle was presented very early on. Okay, so here, this far end would be the drain, this would be the source. Typically, these devices can be manufactured as symmetrical, and so the drain and source can be interchanged. But realistically, to apply or to use a J-FET for an application, there are certain differences. So the drain end could be much heavier doped versus the source end. So it just depends on the application, depends on the kind of JFET. But typically we could just reverse the two terminals, and chances are for like a limited period of time, limited applications, the device would work just fine. Okay, the symbol for both are shown right here. It's a straightforward symbol. You have, sometimes you'll also see something like this. Okay. This is what the book uses, and this is what I have drawn here is something you might find in a different book also. Doesn't necessarily have to be right at one end. You see the gate is pointing towards one end. That's not always the case. Okay, sometimes that arrow is pointing in the center. So if you see a symbol like that, that is for a JFET. So for an N channel FET, arrow is pointing in. For a P channel FET, the arrow is pointing out. Okay, it's pointing out. And the arrows are marked primarily on the gate because of the gate that's actually controlling the flow of current. So current's flowing down, and the gate is controlling how much is going to come down. Okay, so depending on our application, we would control the flow of current, well, depending on our needs. JFETs are primarily used for RF analog applications, sometimes in BiFET devices. BiFET devices combine both BJTs and FETs on the same circuit or the same chip. Sometimes for high-speed devices. One of the characteristics of a JFET is its high input impedance versus a BJT that does not have that much high impedance. When a device has very high input impedance, it requires very low amount of currents to actually work. And so that's a very good criteria in electronic circuits and electronic devices. Good feature to have. Okay. Good so far? Question? Lots of questions. It is. That's what it is. That's what all transistors are. That's a switch. Okay, going on a bit of tangent. Transistors, FETs, they have two primary modes of operation. On, off, so it's a switch, and there's a linear region where you use it as an amplifier. That's it. All digital logic circuits are just switches, right? Zeros and ones. Was that any sort of revelation? Okay, all right. So here we have a JFET, which does not have any voltage applied. Okay, so this is known as a zero bias state. Okay, zero bias state. This is basically the same as the thermal equilibrium that we saw or we looked at in chapter 2. Okay, at thermal equilibrium, at equilibrium conditions for a p-n junction, there is a depletion region that forms, right? And there's a reverse electric field that is generated that stops the depletion region from growing too much. And so it's the same thing. You create a p-type material inside a n-type material. Depletion region forms. With zero bias applied, the channel has a specific width. Right here. Okay. You draw it up correctly. Okay. That is the width and length of the channel. Now, the gates, of course, are connected together. Sorry, not the gates. The p-type material is connected together to form one single gate, and that is also applied zero bias. So the gate to source is applied zero bias, and the drain to source is also applied zero bias. Okay, it's completely grounded. Now, if you reverse bias the gate and the source, what would happen? So VGS meaning the voltage measured at the gate with your reference to the source. Okay, so positive reference is as the gate, negative is at the source. If it goes below 0 volts, meaning you're applying a reverse bias to the PN junction, right? Gate is P-type. So now you're reverse biasing the junction. When you reverse bias the junction, what happens to the depletion region? Shown right here. Depletion region expands, and because depletion region is expanding, the channel width is shrinking. And eventually, if the reverse bias increases, at one point, the depletion region will meet in the middle, resulting in a pinched off channel, meaning no more flow of electrons. Okay, that voltage is known as the pinch off voltage, at which no current would flow. Theoretically. In real life, there's always a small amount of current flowing through. Question? Okay. All right, so zero bias again. VGS is 0. VDS, the drain source voltage, is also 0. Everything is grounded. Now, at this point, it's in equilibrium. There's a depletion region that exists at both sides. If you now decrease VGS, you apply a negative voltage at the gate with reference to the source, it is now being reverse biased. At reverse bias, depletion region increases. Eventually, it will result in a pinched off channel. And a pinched off channel means the device is turned off. Okay, so device turns off, which means that the device was inherently on without doing anything. Okay, so the device is normally on when it's manufactured, and hence it is also known as a depletion mode device. We must apply an external voltage to turn the device off. Okay, we must apply an external voltage to turn the device off. Hence, it is known as a depletion mode device. Yes.
There's no voltage difference, electric potential difference. Does that mean that it's going to be zero current, which means it's off?
The point being made is if VDS is 0, how is it supposed to be on? Well, the point is the gate is actually controlled. So when you say the device is off, it is the gate that is turning it off, the gate voltage. So the next page, the next slide, here we have figures and illustrations where we have VGS may be equal to 0, but you apply a drain to source voltage, and because of the externally applied voltage in electric field, you have current flow from drain to the source. That is at VGS equal to 0. So at VGS equal to 0, if we apply VDS, then we have current flow because we have movement of electrons. Okay. So that is what is meant by on, meaning PN junction is at equilibrium. You must apply an external voltage anyway to get electrons flowing, or electrons and holes flowing in the PN junction. Now you extend that concept of physics to the FET, where you have two PN junctions. The reason it's on is because the channel is open. So channel is open, we say inherently that the device is on. But we must apply a external voltage between the drain and the source for the electrons to flow. But to close off the channel, we must apply an external voltage, which is VG. And when we say device is on or off, It refers to the channel, whether it's on or off. Okay, I think we're out of time. So I'll pick up here again next class on Wednesday. And I will see you all then. I'll be available in my office all day if anyone has any questions. Till 5, 7 to 5.